heating and cooling curves, but first I want y'all to take a look at this simulation. If we have a beaker of water, it's got a thermometer in it, and I'm actually gonna set it down. And underneath, it's got water in it. Now inside we have a thermometer over on the left, and we can see that if we change the water temperature, the thermometer goes up or down, right? So what I'm going to do, I want you to notice quickly, watch the beaker, and right at that point, right that at 0 degrees Celsius, what do you notice? It changed, and it changed into ice, right? So it's not water anymore, it's ice. So I'm going to leave it down there at probably negative 35 degrees Celsius, okay? And so we can see the temperature here, we can watch the mass if we really wanted to as well. And so now over time, we're going to add some heat. We're going to add 250 joules per second. And so we're going to heat it over time. And as soon as I hit play, we're going to graph it. All right. So as we're watching, it's starting to heat up, and you can notice the temperature is changing. And wow, that's moving fast. But now, if we're looking closely, we can see that the water is going away. I'm sorry, the ice is going away and turning into water. So I'm going to pause right there. And this is ice on top, and this is water on bottom. So this is ice water. Now notice the temperature is 0, and it's going to stay 0 even as the ice begins to melt. It's going to stay 0 until all the ice is gone. Once the ice is gone, then the temperature will start to increase. And you notice how it starts to increase and move, and it's just normal water. And the thermometer will increase kind of at a slower pace. And as we get to 100, it will start to boil, and the temperature is now maxed out at 100 degrees Celsius. Okie doke. And so now we can see on this graph, now it's a flat part on the graph as well. So it's nice to see that being graphed over there. Now this is called a heating curve. It's not much of a curve, it's a bunch of line segments, but this is called a heating curve. So we're going to draw one right here in our notebooks. So if we open it on up, we took notes on Unit 3, Lesson 1. So this is going to be Unit 3, Lesson 2. And we're just going to write it down. We're going to call it heating curves. Okay, now there's more to it than this. Well, I mean, there's going to be additional parts that we'll walk through a little bit in a minute, but we just want to learn what a heating curve is. So let's go ahead and draw in the important stuff. So that would be our axes. And on the left side, we're going to have temperature. And that temperature is going to be degrees Celsius. And then on the x-axis, we're going to have time. Now, sometimes reaction progress or something like that. This is just a sketch. Now, I want you to take that, and so we noticed that we had something at a somewhat steep curve, and then it got to here, and then we stopped, and then we got a small flat plateau. It was right here. And then we noticed a different slope of a curve until we got to about here. Notice that it's a different slope, right? Okay. And we got a longer flat part. So if we notice again that this part here and this part here, this one is longer. And now we get to a different one, a different slope. So there are three different sloped parts and there are two plateaus. So a full heating curve will always show those right there. Okay. Now, they could give you just this, right? Or they could give you just this, and you just would look at that, but this would be a full one. All right, so there's a couple things you should be able to note. Two very important points, right here and right here. And now this part is going to be, this would be the boiling point. And this would be the melting point. Now, this section right here, this is where the temperature was increasing, right? So over time, the temperature started to increase, and we imagined our block of ice, right? And so this is where it's ice, and still ice, and still ice, and still ice, and still ice, up till it got to this point, up till it got to the melting point, and then the ice began to melt. So here it is a solid, but here we had ice water. So both the ice and the water were present. Okay, so that's a solid and a liquid. Now, once all the ice was melted, then we got to a very long part that was a liquid. All right, and then we get to a liquid plus a gas, and now this one is a gas. So these heating curves represent different phases. The sloped parts represent the um, pure phases, okay? And then the flat parts represent the phase changes, okay? Now, here we have a phase change here. This is a phase change. And here we have a phase change. All right, very nice. Now I'm going to draw one more time because I don't want it to be too messy. And I'm going to try to draw it right here. And I want to draw kind of the same thing. Oh, I drew that way too long. Okay, so again, we're going to have temperature and time. Now, I want you to write this down. This is super, super important. The kinetic energy is the average speed of the particles. Okay? And kinetic energy is equal to temperature. So this is how we measure kinetic energy, is we just measure the temperature. All right, but the potential energy is the force of attraction among the molecules, among the particles, I'll say, among the particles. Great. So I wrote a whole lot of words down. Okay. There. Get that out of the way. All right. So we're going to look very closely at this one more time. But I want you to try to think we are adding energy the entire time, right? Because we were heating it up. But I want you to identify which ones were kinetic energy, which ones were potential energy. All right. So from here to here, we were adding kinetic energy. How do we know this? Because we increased the temperature, and the temperature change represents kinetic energy. Okay, we can see a change in temperature, a change in the y-axis. Over here, between here to here, we can also see a kinetic energy change, right? Because we have an increase in the temperature. And again, here, logically, that means that we have kinetic energy is being added here, right? But in these plateaus, the reason why we have plateaus here is that the energy that's being added is not going into speeding up the particles, but it's going into changing the phase. And so that is dealing with the force of attraction among the particles right here. All right. So we have potential energy here and here. All right. We are using the potential energy to either loosen the particles. Here, we are loosening the particles. Or here, we're not going to loosen the particles. We are going to separate the particles. All right. So, kind of cool. It's nice to have all those heating curves and stuff already there and know exactly kind of what we're getting at. All right. So we can just, oh, and if we were to draw a particle diagram, I'm going to draw a particle diagram of, you guys know how to draw particle diagrams of solids, liquids, and gases. We've done that before. But what if we were to draw a particle diagram of this place right here? What would a solid and a liquid look like at the same time? Well, take my advice, draw a liquid like you normally would, and let's draw that block of ice, right? We've got a block of ice on top of it. So let's draw an organized thing that's floating on top of it. So you have a mixture between organized and disorganized right there. And so that would be a nice particle diagram here. Here we would have some particles. So you would still have a liquid, right? It's a liquid plus a gas. So still draw your liquid, but we also have gas particles as well. All right. Everybody see that? I hope that's great. And that is your heating and cooling curves lesson. Have a great day.